Hey everybody, today we're going to be talking about conservation momentum. So first I'm just going to kind of go over the conservation momentum equation, just in case you haven't seen it before. So the first thing we have here is the accumulation term for the momentum. That's like the amount of momentum that accumulates within our system, within the control volume. The second term here is our flux term. This is just like the flux term in the conservation of mass equation that we did prior. This is our external force. These are viscous forces, pressure forces, body forces. The left side has to equal the right side. That's just kind of how the conservation momentum works. Okay, so now we're going to kind of talk about this problem over here that I kind of have written out, in which case we have a jet of water that sprays onto some object here that splits up the water jet into two velocities that kind of conform with this object here. So this is our diagram. It's not the prettiest, but it'll do for what we're trying to do. Next, we're given our volumetric flow rate at 0.1. So we're given how much water comes out of this hose or this jet stream here. We know the area of this hose or jet stream here. We know that the density is going to be uniform throughout this whole thing. And we're given the angles theta and theta 2. As well as we know that there is no gauge pressure, so pressure 1 equals pressure 2 equals pressure 3. And we also know that this Q2 stream is 1/4 of the entire volumetric flow rate, and this Q3 is 3/4 of the entire volumetric flow rate. And we're trying to find the external force in both the x and y direction. And we're assuming that it's steady state, which means we can get rid of this value here. That there's no viscosity, so we can get rid of our viscous term there. And that we're neglecting height when we try to do Bernoullis, or if we do Bernoullis, and we're going to neglect the body forces, which just means we're not going to worry about the weight of the water itself. We're just worrying about the momentum caused by the change in velocity, essentially. And then also I'm going to get rid of this pressure term because we have stated that gauge pressure equals 0, or that P1 equals P2 equals P3. So now our next step is to solve the Bernoullis to figure out the relation between V1, V2, and V3. So as we can kind of see here, I kind of have this written out already. But you have the general Bernoullis equation where the pressure terms get gone and the height terms go away. In which case we just have V1 squared over 2g equals V2 squared over 2g, which obviously shows that V1 equals V2. Throughout the same process, we can also prove that V3 is also equal to V1 and V2. So it leaves us with the next step of just writing out this equation in both the x direction and the y direction. So we start with the x direction. We get integral control surface of rho v dot v dA is equal to sum of force external, which that gets equal to, so now we're going to do it about each surface. So this first surface we'll do becomes negative q, which remember q equals v times a, times rho times the v1, and we can actually find v1 as equal to q divided by a, q1 divided by a1. In this case, we're trying to do the x direction of q1, so it's, or v1, so it's v cosine theta 1. Then we're going to add the q2, which, like we said, is 1/4 q1. So rho v2 cosine theta 2 plus 0, because this third velocity is just straight in the y direction, is equal to the force in the x. And we can do the same thing with the y direction, where this is equal to negative q1 rho v1 sine theta 1 plus 1/4 q1, because that's q2, rho v2 sine theta 2 plus 3/4 q1, which again, that equals q3, times rho v3, which equals your force in the y. And then doing this, we now have fx and fy, and now we've figured out what we're trying to here. Yeah, so hopefully that helps you kind of see how to use the conservation of momentum equation a little bit better. This here, just to clarify, is each integral evaluated at each surface where it was negative going in, positive going out. That's why we have a negative here and here, but a positive here, 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 and here. Yeah, I think that's really the only trick to solving this. Hopefully you found this video helpful. Until next time.